Welcome to Entropy Part 2. In the first video lecture, we gave an introduction to entropy, and we talked about how to calculate the change in entropy for various processes. In this lecture, we're going to do some statistics, and we're actually going to find out what entropy really is, what it really means. And we're also, finally, going to find out what temperature really is. Okay, now on to what entropy actually is. Entropy connects the microscopic world to the macroscopic world. For example, imagine I have a box with some gas molecules zipping around inside of it, as depicted here on the left. The microstate of that system is a description of what every single molecule is doing. But oftentimes, I don't need to know what every molecule is doing. So instead, I'll think in terms of the macrostate. What's the overall property of this gas? Or maybe I have a solid depicted on the right. This solid is made up of a bunch of atoms in a lattice, and they're wiggling around. If I knew what every single atom was doing at every time, that's what we would call the microstate of the system. But maybe I don't need to know what every atom's doing. I just need to know, its temperature and whatnot. So oftentimes we talk about macroscopic parameters like the density of a solid, the pressure of a gas, the temperature of a gas, or the entropy of a gas. So I don't have to know what every single molecule is doing to know the pressure in my gas. That is the macrostate. That's a macroscopic property. Knowing what every individual molecule is doing, that's the microstate. The entropy is the thing that makes the connection between microstates and macrostates. But instead of talking about gas, let's take a simpler system. Imagine I have 4 coins, and each of those coins has only 2 things it can be. It can be heads or tails. And if I know whether each coin is heads or tails, I have a complete description of my system. All right? So imagine I have my 4 coins. How many arrangements of heads and tails are possible? For example, one possible arrangement is all of the coins are heads. Another is coins 1, 2, and 3 are heads, coin 4 is tails. Or how about coins 1, 2, and 4 are heads, and coin 3 is tails, and so forth. How many different arrangements are possible? Pause the video and think about this, and come back when you have an answer. Well, hopefully the answer you got was 16, because that's the correct answer. How do I know that there's 16 possible ways? Well, I just write down all of the possible ways and I count them, and there's 16 of them. If you know a little bit about computer science, you may realize what I'm doing here is I'm just counting here in binary. If you replace the H's with zeros and the tails with ones, I'm just counting in binary to find the total different number of possibilities. And, there are 16 different numbers you can make with 4 bits. Another way to think about it is coin 1 has 2 options. It can be heads or tails. If I pick one of those options for coin 2, or coin 1, coin 2 still has its 2 options. So with 2 coins, there's 4 different ways I can arrange them, heads or tails. Well, if I add another coin, that adds 2 more possibilities. Well, it doesn't add 2 more possibilities, it multiplies 2 more possibilities. So whatever possibilities I have for the first 2 coins, I can do any of them with the third coin being heads or the third coin being tails. So now that doubles the number of possibilities. If I add a 4th coin, that doubles it again. So the number of different arrangements, the number of different microstates for my coins is 2 to the 4th, or 16. Okay, so this is what we call the microstate of our system. That's knowing exactly what each molecule is doing. Or for our penny system, it's knowing exactly which coins are heads and which ones are tails. We know the properties of individual pieces of our system. Now, of those 16 arrangements, how many of them have exactly 2 coins heads up? Think about that, pause the video, come back when you have an answer. The correct answer is 6. 2 coins heads up is what we call the macrostate. I don't know what the individual coins are doing. All I know is that overall there's 2 coins that are heads up. So what this question is asking is, for the macrostate of 2 coins heads up, how many microstates are there that correspond to that macrostate? Well, I can write down all the microstates, and I can count them, and I say, oh, there's 6 of them that have exactly 2 heads. That can get really tedious as the number of coins goes up. It gets really tedious really fast. So is there another way I could figure out how many microstates correspond to the macrostate of 2 coins heads up? Well, yes, there is. I've got my 4 coins, and I want to pick 2 of them to be heads up. How many possible choices do I have to pick the first coin to be heads up? There's 4 choices. There's 4 coins. Let's say I pick coin number 4. Okay? Now I need to pick another coin to be heads up. How many choices do I have? Well, there's 3 coins left, so I have 3 choices. Let's say I choose coin number 2. Okay? All right. So there's 4 times 3 different ways I can choose 2 coins to be heads up. Wait a minute. 4 times 3 is 12. We said there's only 6 microstates. But there's 2 different ways I could have chosen this same microstate. I could have chosen coin 4 and then coin 2, or I could have chosen coin 2 and then coin 4. So I have overcounted the number of microstates by a factor of 2. So if I divide by 2, I get 6. Here's a question. If I drop 4 coins on my desk and they land randomly, what is the probability that exactly 2 of them will land heads up? Pause the video, come up with an answer, and then come back. The correct answer is 37.5%. How do I calculate that? Well, each of those different microstates is equally probable. There's 16 different microstates. I'm just as likely to get one versus another when I drop my coins. But 6 of those microstates correspond to the macrostate of 2 coins being heads up. So 6 out of 16 times, I would expect to get 2 coins heads up. So the probability of getting 2 coins heads up is 6 over 16, or 0.375, which is 37.5%. So again, 2 coins heads up, that's my macrostate. I have 16 different microstates, and 6 of them correspond to the macrostate of 2 coins heads up. So here is a plot, again, the same plot of the probability of getting 0, 1, 2, 3, or 4 coins heads up, right? And the probability, I just take the number of microstates that correspond to each macrostate. There is 1 microstate that corresponds to no heads up. So 1 chance out of 16, I will get all coins tails. And there is 1 microstate that corresponds to all coins heads up. So 1 out of 16 times, I expect to get 4 coins heads up. But there's 4 ways to get 1 coin heads up. So 4 out of 16, or 1/4 of the time, I would expect to get 1 coin's heads up. Or similarly, I would expect 1/4 of the time to get 3 coins heads up. The most probable outcome is 2 coins heads up, because there are 6 different microstates. 6 of my 16 different microstates correspond to the macrostate of 2 coins heads up. So I expect 6 out of 16, or 3/8 of the time, to get 2 coins heads up. Well, entropy is related to these microstates. So the entropy of a given macrostate is just Boltzmann's constant times the natural log of the number of microstates that correspond to that macrostate. All right? So the idea here with the second law of thermodynamics, as I shake up my coins, I should move to a higher entropy state. The state that has the macrostate that has the most microstates affiliated with it is the most likely one to show up. And so the highest entropy state is what we expect to get. Now, which macrostate of the 4 coins has the highest entropy? Think about this, pause the video, and come back when you've got an answer. The correct answer is 2 heads, right? Because 2 heads has the most microstates. Most microstates means the natural log of a bigger number is bigger than a natural log of a smaller number, so we're going to get higher entropy. So once again, here's the probability of getting 0, 1, 2, 3, or 4 heads. Those correspond to 1, 4, 6, 4, and 1 different microstates that correspond to each of those macrostates. If I take the natural log of the number of microstates that corresponds to each macrostate and multiply by Kates-Boltzmann, I get the entropy. So here's a plot of the entropy. All right? And so the most probable state, macrostate, is the one with the most microstates, but the one with the most microstates is the one with the highest entropy. So higher entropy means higher probability. Now, entropy is different things to different people. In thermodynamics, we define entropy to be Boltzmann's constant times the number of microstates that correspond to a given macrostate. But they also use entropy in information systems, in computer science, information science. For example, you can use calculations of entropy to decide how much you can compress a file without loss. So for example, imagine I have a big text file and I want to compress it into a zip file. How much can I compress it? Well, calculate the entropy of the file. If I have all zeros, that's a very low entropy state, and I ought to be able to represent that with a much smaller number of bits. But if I have a random string of ones and zeros with about equal numbers of ones and zeros, that's a high entropy state. There's lots of microstates that correspond to that macrostate. That's a high entropy state. You won't be able to do compression on that. Okay? You can also think about entropy in everyday life things, like, for example, parallel parking. Why is it so much harder to park a car than it is to pull out of a spot when you do parallel parking? Well, you can think of that in terms of entropy. There is a small number of ways for your car to be parked, a large number of ways for it not to be parked. So parking is like going to a lower entropy state. You can think of it that way. That's what makes it difficult. You can also do a hand-waving kind of characterization of the clutter in your room. Like if you take all the books off of your bookshelf, there is a large number of ways you can distribute them randomly around the room. That is a high entropy state. There's a much smaller number of ways you can orderly arrange your books on the bookshelf. So that's a low entropy state. And that's why people sometimes talk about entropy as a measure of disorder. The second law of thermodynamics is a law of thermodynamics. So thermodynamic systems, what are thermodynamic systems? The second law of thermodynamics only applies to thermodynamic systems. So we need to know, what is a thermodynamic system? Well, a thermodynamic system is one where each microstate is equally possible. All right, so when we drop our coins on the floor, there's all these different microstates. Each one is equally possible. All right, that's our random equal a priori assumption. So our coins do fit that definition, but there's another thing you need to have in order to have a thermodynamic system. You have to have a very large number of particles. So our 4 coins do not constitute a thermodynamic system. Now, we can't, as the number of coins get bigger, as we approach a thermodynamic system, it gets really hard to write down the number of ways you can flip a coin by hand. So let's think about this more mathematically. Let's imagine I have n coins and k of them are going to be heads up. How many different ways can I have k coins out of my n coins heads up? Well, in the numerator, what we're saying is, look, the first coin I pick to be heads up, I have n different choices. For the second one, I have n minus 1 choices. For the third coin, I have n minus 2 choices, and so forth, all the way down to the last coin that I pick, I have n minus k minus 1 choices. All right? But remember, we overcount when we do that. Because I could have chosen those same k coins to be heads up, but I could have chosen them in a different order and gotten the same microstate. So the denominator says, oh, when I have my k different coins I'm choosing, which one I chose first, I have k different choices for that, so I've overcounted by a factor of k. But then I have k minus 1 choices for picking the second one, so I've overcounted by a factor of k minus 1 for that one, and so forth. And so that's what the denominator is all about. Now, you can rewrite this as n factorial over k factorial times n minus k factorial, right? So the numerator is like n factorial, but I cut off at a certain point. I don't go all the way down to 1. So n factorial over n minus 1 k factorial gives you the numerator. And then the denominator, of course, is just k factorial. So without having to write down all the different ways you can arrange coins, if you had 50 coins and you wanted to calculate, the number of ways that you could have 10 of them heads up, that would be really tedious to do, writing down all the different ways. You can use this instead to calculate the number of ways without having to write them all down individually. Well, it turns out as we go to more and more coins, even calculating factorials gets hard, and your calculator won't be able to do it. And so it turns out that there's an approximation you can use for this that is good in the limit of large numbers of when n is really big. So I'm going to make some plots where I'm going to show what happens as we go to more and more coins. And the blue dots represent calculating directly, and the green is that approximation. So for a small number of coins, the approximation isn't great, but it gets better as we get larger numbers of coins. But that's not important. What I want you to see is what happens as we go to larger and larger numbers of coins. So if I have 4 coins, right, and we plot the probability of having different numbers of heads, we get this right here. As I go to 10 coins and 100 and 1,000, notice this curve gets much, much narrower. As I go to 10 to the 4th coins, my computer can't do the factorials anymore, so I only have the approximation. But I can use that approximation to go to higher and higher numbers. By the time I get to 10 to the 23rd coins, something on the order of Avogadro's number, that curve is just a spike. So what that is saying is, in the limit of a large number of particles, probability becomes actuality. If I had 10 to the 23rd coins in a box and I shook it up and opened the lid, there is just almost no possibility that I will find a significant deviation from half of the coins heads up, half of the coins tails. All right? So in the limit of a thermodynamic system, you just get something really, really close to half coins heads, half coins tails. Okay, so now we've talked about possibilities for different coins. Now let's divide our coins up into 2 systems. So instead of having 4 pennies, I'm going to have 2 pennies and 2 dimes. And we're going to use that to simulate heat flow. All right, so now we're not going to allow all 16 possibilities. I'm going to let heads up represent a unit of energy. So I'm going to start with 2 units of energy. I have my 2 pennies are heads up and my 2 dimes are tails. So the pennies have all the energy and the dimes have no energy. And we're going to let heat flow. So if I have a coin that's heads up next to one which is tails, I can roll the dice, randomly decide to swap the energy. So now the dime has the energy and the penny doesn't. And we're just going to do that over and over again, randomly exchanging energy. And after I do that for a long time, I'm going to come back and I'm going to say, how's the heat distributed? Right? So this is modeling. Imagine I have something that's hot and something that's cold, and I put them together. So I have something that has lots of thermal energy, something that has less thermal energy. I put them together, and I let the heat flow between them. What am I going to find after a long time? Okay? Well, let's think about this with our pennies and dimes. I'm going to let X represent the number of pennies that are heads up. So 2 coins will be heads up. But the number of pennies that are heads up could be 0, 1, or 2, right? Like the pennies could have all the energy, or the dimes could have all the energy, or it could be split. Now, the probability of having X pennies heads up is just the number of ways I can arrange my coins with that number of pennies heads up divided by 6. Why 6? 6 is the total number of ways I can arrange my coins with 2 of them being heads up. So there's 6 ways I can arrange my coins such that 2 of them are heads up. How many ways can I arrange them such that X of those 2 coins are pennies? 0, 1, or 2 of them are pennies, right? That's what this probability is. How do I find how many ways I can arrange my coins with 0, 1, or 2 of them being pennies? Well, all I have to do is I have to say, well, if I have X pennies that are heads up, how many ways can I arrange my 2 pennies with X of them being heads up? And how many ways can I arrange my dimes such that X pennies are heads up? All right, so W sub P is the number of ways I can arrange 2 pennies with X of them being heads, and W sub D is the number of ways I can arrange 2 dimes such that 2 minus X of them are heads, right? Because X is the number of pennies that are heads. Well, let's write down the different arrangements. Here are the 6 different arrangements of my coins that have 2 coins that are heads up. Notice only one of them has 2 heads as pennies. So in only one of them do the pennies have all of the energy. So there's one way I can arrange two pennies such that they're heads up, and one way I can arrange two dimes such that they're tails. The product of those two is 1. There's only one way I can have all of the energy with the pennies. So the probability, after I let the coins flip around randomly, the probability of looking and finding the pennies having all of the energy is 1 out of 6. Similarly, the number of ways that I can have the dimes have all the energy, well, there's one way to arrange two pennies, both tails, one way to arrange dimes, both heads. The product of those two is just 1. There's one way to have the dimes have all the energy. So the probability of having 0 pennies that are heads up is 1 out of 6. There's 4 ways where I can have 1 penny heads up and 1 dime heads up. All right, and you can think about that. You can break it into pieces. I can say, well, look, if I have 2 pennies, there are 2 ways I can arrange them such that one of them is heads up. If I have 2 dimes, there are 2 ways I can arrange them such that there are exactly one of them heads up. So the ways I can arrange the whole system is W pennies times W dimes, which is 4. So there's 4 overall combinations that correspond to 1 penny being heads up and 1 dime heads up. So if I let the energy pass back and forth randomly, and I open up my box and look, there's 4 out of 6 chances that I will find the energy split equally among the pennies and the dimes. Now, once again, here are the probabilities of finding none of the energy with the pennies, half the energy with the pennies, all of the energy with the pennies. And if I then take the entropy of these different states, I find that the highest, the most probable state is the one with the highest entropy, and that's what I'm most likely to find. But if I close the lid and let heat flow around a little longer, there's a possibility I open it up and it goes down to a lower probability state, one with fewer microstates, which means lower entropy. But that's okay because 2 pennies and 2 dimes is not a thermodynamic system. So let's see what happens when I have more coins. Here's what I get if I have 40 pennies and 40 dimes and exactly 4 of them are heads. So here's the probability of having 0 pennies heads all the way out to 4 of the pennies are heads. So all of the energy with the pennies. And you see the highest probability is splitting the energy half and half because my 2 systems have equal heat capacity, right? They have equal capacity to hold heads. Let's increase. There's 100 pennies and 100 dimes, 1,000 pennies and 1,000 dimes, 10 to the 4th pennies and 10 to the 4th dimes, 10 to the 3rd of them being heads. Once again, my computer couldn't calculate this anymore, so now we just have the approximation. But with that approximation, we can go higher. And here we are, 10 to the 6 pennies and 10 to the 6 dimes. Here's 10 to the 23rd pennies and 10 to the 23rd dimes, sharing 10 to the 22nd units of energy. 10 to the 22nd of them are heads. And notice we get a spike. So if I start with some energy with the pennies, some energy with the dimes, and I let that move around, once I reach equilibrium, I'm going to have half the energy with the pennies, half with the dimes, and there is just a vanishing probability that I will ever look at my system and see that it has varied significantly from that. So we basically go to the state which is most probable, and the state which is most probable is the macrostate that corresponds to the microstate, that has the most microstates that correspond to it. And in the limit is I have lots and lots of things. In the thermodynamic limit, the probability of varying from very far away from that most probable state is very small. And so then the second law works and we say, the system is going to go to the state of maximum entropy and it's going to stay there. It won't just randomly go down to lower entropy. But why do we talk about entropy instead of W? Right? W is the number of microstates that correspond to a given macrostate. Well, why do we take the natural logarithm of that? Why is that convenient? Well, first of all, this number of ways can get very, very, very large. And taking the logarithm of a big number tames it. All right? But also notice, when we were talking about the heat flow from our pennies to our dimes, the number of ways to arrange that energy turned out to be the product of something that had to do with the pennies and something that had to do with the dimes. When we do a logarithm, the logarithm of something times something can be divided up as the logarithm of the one thing plus the logarithm of the other. So by taking the logarithm, that allows us to break up this property into a property of system 1 and system 2, rather than being forced to think about both of them together at once. So when we talk about entropy and use the logarithm, we can talk about the entropy of object 1 and the entropy of object 2 and how they change as they exchange heat and come into equilibrium. We'll talk about the reason for Boltzmann's constant momentarily. So, equilibrium. In equilibrium, we go to that high entropy state. So basically, the entropy of our system is the entropy of the pennies plus the entropy of the dimes, right? And as energy goes back and forth, we are going to reach equilibrium when we have maximized the entropy of the system. So how do I maximize the entropy of the system? Well, let's let some amount of heat, dq, move from the pennies to the dimes. And we're going to see what happens as we move that energy back and forth, what happens to the entropy of our system. All right? So the change in the total entropy of the system is going to be, we're going to take some heat out of the pennies, so the amount that the entropy of the pennies will go down by d pennies over dq, and the amount of entropy of the dimes will go up by d entropy over dq. Now, to maximize something, we take the derivative and we set it to 0, right? So we get maximum entropy. We come into equilibrium, reaching maximum entropy when ds dq is equal to 0. So equilibrium is when ds dq is equal to 0, but remember, ds dq was negative the derivative of the entropy of the pennies as I add heat to it, plus how the entropy of the dimes change when I add heat to it. So entropy is when those two derivatives are equal. When adding a little bit of heat to the pennies changes the entropy of the pennies by the same amount that adding that little infinitesimal amount of heat to the dimes would change the entropy of the dimes. But equilibrium is when the temperatures are the same. So maybe temperature is just derivative of entropy with respect to Q, because that's the thing that two things have in common when they're in thermal equilibrium. Well, it turns out if you define temperature to be that, temperature goes down as you add heat. So instead, we're going to define temperature to be 1 over the derivative of entropy with respect to heat entering the system. Then, when two things have the same entropy change per heat coming in, they have the same temperature and they're in thermal equilibrium. Okay. Now, then we have our equation, right? If we rearrange it, we have the equation that we gave in part lecture 1 in order that we use to calculate entropy changes. That's where it comes from. Now, why do we put a K Boltzmann in our definition of entropy? Well, because if we didn't, then we would have to put it in our definition of temperature. So basically, we put it there, right? We came up with the temperature scale and then understood entropy, and we said, well, look, if we put a K Boltzmann into our definition of entropy, then temperature doesn't have a weird constant. It's just the 1 over the derivative of entropy with respect to Q. Okay. Now, remember in lecture 1, we had 3 questions. I gave you these equations and we said, where does this equation come from? Why do you get a bigger entropy change when heat flows in at low temperature and a smaller one when the same amount of heat flows in at a higher temperature? And both of those questions I said we couldn't answer at the time. The third question, what if the process is not reversible? We said, we'll just come up with a reversible way to do it. And we answered that question. Well, now we can answer question number 1. We know where the equation came from. It came from our definition of entropy and our definition of temperature. So we define temperature in terms of entropy change and rearrange things, and we get that equation. So we've answered that question. What about question number 2? Let's answer that one right now. So imagine I have a bunch of coins, all right? In this example, I've got 1, 2, 3, 4, 5, 6, 7 coins, 8 coins. So Let's take the macrostate where I have no coins heads. So k is equal to 0. How many different ways can I realize that macrostate? Or in other words, how many microstates correspond to that macrostate? 1. W is equal to 1. There's only one microstate. If I take the entropy of that macrostate, that's just the natural log of W. I'm leaving off Boltzmann's constant because my numbers will look much nicer. So for my penny example, right now I'm changing my definition of entropy so it doesn't have Boltzmann's constant. But for a thermodynamic system, you need Boltzmann's constant, so just be aware. Anyway, take the natural log of 1 and I get 0. And I'm going to define this state to be the 0 temperature state, right? This is absolute 0. There is no energy in the system. Well, let's add 1 unit of energy. Let's let one of the coins be heads. All right, so now I have the macrostate with 1 coin being heads. There are 8 different microstates that correspond to that, right? I have 8 choices for which coin will be heads. If I take the natural logarithm of 8, I get 2.074, okay? Now, how much did the entropy change with changing K? Well, we just take the entropy we have now minus the entropy we had when we had 1 less unit of energy, when K was 1 less, and there's ds dk. We take 1 over that, and that's our temperature, okay? So our temperature increased. Now, what if I have 2 coins? How many different ways how many different microstates correspond to 2 coins being heads up? Well, I had 8 choices for the first coin, 7 for the second, but I've overcounted by a factor of 2, so the number of ways has gone up by a factor of 7/2. So there are 28 microstates of my 8 coins that correspond to 2 coins being heads up. So the logarithm of 28 is just the logarithm of 8, which we had before, plus the logarithm of 7/2, which is 3.3322, ... So our entropy was originally natural log of 8. It went up by the natural log of 7/2. Here's, once again, the beauty of the logarithms. These numbers are not getting enormous. Also, we can separate it out into the entropy we had by putting 1 coin in, plus additional entropy because we added another unit of heat, okay? And the derivative of entropy with respect to K, it's the entropy we had with 1 unit of heat, and then we subtract that from the entropy we have now with 2 units of heat. And we subtract them and we get 1.2528 ... And then 1 over that is the temperature. Notice, as I went from 1 coin heads to 2 coins heads, the number of microstates, when I went up from 0 to 1, the number of microstates went up by a factor of 8. When I went from 1 to 2, the number of microstates only went up by 7/2. So the change in entropy was smaller when I started at a higher temperature. So going from 0 temperature to 0.48 was a bigger change in entropy than going up the next step. If I have 3 coins that are heads up, that's 56 microstates that correspond to that macrostate. We go up from what we had before by a factor of 6/3. All right, and so our entropy is just the natural log of 56, which is the natural log of the number of microstates we had before plus natural log of 6/3, because we now have a factor of 6/3 more microstates. And you can find the change in entropy by going up by 1 unit of heat, and our temperature then is 1 over that, all right? And so you see, as we add heat and the temperature goes up, each step we increase the number of microstates by a smaller factor, which means the entropy goes up by less. So that is where we get our 1 over T in the entropy, all right? So yeah, as temperature goes up, the amount of entropy change that we get by adding heat goes down. So let's take a look at this. So here's 8 coins, and here is the probability of having 0, 1, 2, 3, 4, 8 coins heads up if I drop them on the floor randomly. All right, here are the number of microstates that correspond to each of those macrostates, right? There's 70-something different ways. What did we say in our chart? Oh, exactly 70 different ways that I can have 4 of them heads up, and only one way to have them 0 heads up or all heads up, right? Now, if I take the natural logarithm of that, I get something proportional to the entropy. So here's the entropy for my 8 coins, all right? Now, when does the entropy increase the most? Look at this graph. When does the entropy increase the most? When I go from 0 to 1 heads, from 1 to 2 heads, and so forth. Come up with your answer. Pause the video, come back when you've got an answer. All right, the correct answer is when we go from 0 to 1 heads, right? When I go from 0 to 1, the entropy changes by a lot. When I go from 1 to 2, the entropy doesn't change as much. When I go from 2 to 3, the entropy changes even less. So we get the most entropy change at the lowest temperature. So the temperature of our coins, right, is just 1 over the change in entropy. And so the change in entropy, notice, is bigger when I add heat at lower temperatures. All right, so here is the temperature of our coins for, 0 heads. 0 heads, sorry, this is dsdk. This is 1 over the temperature, right? For 0 coins, that's infinity, and then it goes down. If we take 1 over that, we see the temperature for having 0 coins heads up is 0, absolute 0. And as we add more heat, the temperature goes up. So here's 100 coins, here's the probability, here's the number of microstates, here's the entropy, and then if we take the change in entropy per, adding 1 more unit of heat, we get this, and 1 over that is the temperature. And yeah, so there you have it. Now, why can you not reach absolute 0? If we go back, notice here that 1 over t in our equation, that in order to get to absolute 0, that last little bit of heat we pull out causes an infinite change in entropy. So if I pull out that last little bit, that last little dq at absolute 0 temperature, that 1 over t in our entropy equation says that I have to decrease the entropy in that system by infinity, which means the entropy somewhere else has to go up by infinity. Therefore, the second law of thermodynamics says, you can't get to absolute 0. Okay, I did a little simulation of heat flow. So I've got some pennies. This time I have fewer pennies and more dimes, so they have different heat capacities and whatnot. So in the end, they won't have equal amounts of energy. And I started with a bunch of the pennies being heads and none of the dimes being heads. And then what I did is I just did a random coin flip. If a penny's next, or if a heads is next to a tails, they can, randomly decide whether to swap the energy. And so up here in the upper left-hand corner, you see the number of pennies that are heads. So K is the number of heads. And then I have the natural log of the number of microstates for those pennies that have that many pennies heads, right? So basically that's the entropy of the pennies. And then I have the same thing for the dimes, the number of dimes that are heads up and the entropy of our dimes. And then I can calculate the temperature. How much does the entropy change when I add 1 more heads, right? And so I've calculated a temperature for the pennies and a temperature for the dimes using that definition of temperature. Okay, and notice initially the pennies have a temperature, the dimes have a very low temperature because they're at the 0 entropy state. All right, their temperature could be 0 depending on whether, right, because this is not a thermodynamic system. I have a finite number of dimes, and so where do you put the 0? Is that with 1 dime, -1 dime, anyway? But let's let the simulation go. So here we go, energy's randomly exchanging. And notice the temperature of the pennies goes down, the temperature of the dimes goes up, the entropy of the pennies goes down, the entropies of the dimes goes up. Because their heat capacities are not the same, they will not go to the same energy. So we won't have the same number of heads among the pennies and the dimes. They won't have the same entropy. But once they reach equilibrium, they will have the same temperature, which means they have the same derivative of entropy with respect to heat coming in. That if I flipped one more penny to heads, the entropy change I would get from that would be the same that I would get for the dimes if I flipped one more dimes to be heads. All right, so I run the simulation, and that's kind of cool. You see random stuff happening just like you expected. But now let's plot. As I did the simulation, I saved different quantities, and we can plot them. So here is in red the number of pennies that are heads, and in blue the number of dimes that are heads. And as time goes by, the number of pennies goes down, the dimes go up. There's random fluctuations, but they're approaching sort of, a steady state. Now, in the thermodynamic limit where I had an infinite number of coins, right, that noise would shrink down to nothing. But there's some random noise, but they've reached some sort of asymptotic behavior where there's, on average, a certain number of dimes that are heads and a certain number of pennies. They're not equal because the two systems don't have the same heat capacity. There's more dimes than pennies, and so there's more dimes that are heads than pennies that are heads. All right, and here's kind of a smooth curve showing in the thermodynamic limit what you would calculate would happen. Okay, here's the temperature of the two, right? I used my definition of temperature, calculated the temperature, and notice as time goes by, eventually they approach the same temperature. Here's the amount of entropy. The entropy of the pennies in red goes down with time. The entropy of the dimes goes up. But asymptotically, they approach a state where the total entropy of the two of them in black reaches the maximum possible entropy. What about volume? When we did our ideal gas, we said entropy can change when the temperature changes, but entropy also changes at constant temperature when the volume changes. Well, you can think of it this way. Imagine I have 8 boxes that I can put my pennies in. All right, how many ways can I choose to put where to put the first coin? If I have m boxes, I have m different ways to choose. All right, how many ways do I have to choose where to put my next penny? Well, if I allow more than 1 penny per box, I still have m different ways. So the number of ways I can arrange 2 pennies in my boxes is m times m. All right, if I add a third penny, I have another factor of m possible ways I can put them in there, and so forth. All right, so the number of ways I can put pennies into my boxes is m to the n, where m is the number of boxes and n is the number of pennies. Well, entropy is K Boltzmann times the natural log of the number of microstates for the macrostate, which in this case is the number of boxes raised to the number of pennies. All right, so I can use another identity for logarithms where I can take an exponent and move it out in front. So nk Boltzmann times the natural log of the number of boxes. So the entropy, well, nk Boltzmann is just number of moles times the ideal gas constant r. So this is just nr times the number of natural log of the number of boxes. So the change in entropy as I change the volume, as I change the number of boxes, is just nr times the natural log of the final number of boxes minus nr times the natural log of the initial number of boxes. I can use a trig identity again and combine that. That's nr times the natural log of the ratio of the number of boxes in the end minus the number of boxes I started with. But number of boxes, that's just proportional to volume. So the change in entropy is just nr times the natural log of volume final over volume initial. That's exactly what we found when we did the ideal gas entropy. Right there. So same thing works. We're still talking about microstates and macrostates. So volume and energy together, right? So the change in entropy, the number of microstates that correspond to a macrostate, there's a term that goes with the volume, right? Which is number of boxes raised to the number of pennies. And then we have a piece that goes with, sure, you've got the pennies arranged in the different boxes, which ones are heads and which ones are tails. When we calculate the entropy, it's just Boltzmann's constant times the natural log of that. Once again, I can separate that out using identities for natural logarithms into an entropy piece that has to do with the volume and an entropy piece that has to do with the temperature or energy. And so basically delta S is this volume piece plus an energy piece. And remember in lecture 1, on entropy. We talked about for any ideal gas change, you can find the change in entropy with this equation, and there's a part of it that has to do with volume and a part of it that has to do with temperature or energy. So it all works out. So what is temperature? Equilibrium is the most probable state. It's the macrostate that has the most microstates associated with it. In the thermodynamic limit, probability becomes certainty. So you're not just most likely to be in that most probable state. You're going to be very close to that most probable state, always. The most probable macrostate, whoops, there's a typo there. The most probable macrostate is the one with the most microstates associated with it. And entropy is a logarithmic representation of the number of microstates for a macrostate. So therefore, the equilibrium state, which is the most probable state, is the highest entropy state. So equilibrium is the macrostate with the highest entropy. But entropy is maximized when the change in entropy of one object when some heat flows out of it is equal and opposite to the change in entropy of the other object when the same heat flows into it. So equilibrium is when the derivative of entropy with respect to the heat entering is the same for the two objects. Mathematically speaking, in equilibrium, ds dq is the same for both objects. Two objects in equilibrium have the same temperature. So having the same temperature must be equivalent to having the same derivative, ds dq. But to make temperature go up when heat enters, we define temperature to be 1 over ds dq. So there you go. That's what temperature is. Temperature is the derivative of entropy, 1 over the derivative of entropy with respect to heat entering the system. Now you know what temperature is. Now you know what entropy is. You are one of a very elite group of people who know those two things. So once again, the second law of thermodynamics, there are no perfect heat engines, or equivalently, you can't get to absolute zero, or equivalently, the entropy of a closed system can't decrease. This is related to the fact that if you shake a big box with lots and lots of pennies, there's just no way, the probability is very small that you'll end up with all heads, or even wander very far from half heads, half tails. The entropy of a closed system can't decrease because the entropy can't decrease. You can't get to absolute zero. ds dq goes to infinity. So pulling that last bit, infinitesimal bit of heat out would require the entropy somewhere else to go up by infinity. And that's the end of our discussion of entropy.